solving electrical circuits to find currents and voltages is very important. And one of the most important laws that can be used for this purpose is called Kirchhoff's laws. It's actually a set of two laws. One is the junction rule, where the currents flowing into the junction should be equal to the currents flowing out. The other is the loop rule, where if you take the total potential drop through a closed mesh, it should add up to zero. Well, let me get into this with a simple circuit. Now remember, this circuit could have been solved without Kirchhoff's laws. We could have just used Ohm's laws. But for the purpose of understanding, I'm going to use this very simple circuit. So you have a battery coming up there, which is the source of EMF. And connected to that battery, we have a single resistor. So here is the resistor that's connected to it. And remember that current always flows from positive to negative of a battery. So in this case, we can show the direction of the current. There is the positive, there's the negative of the battery. And then, well, this side is supposed to be the positive. The left side is the positive. I'll change that. The voltage provided by the battery is V volts. And the value of the resistance is R ohms. Okay? V volt and R ohms. And the current flowing is I ampere. And we're going to consider the loop in the counterclockwise direction. We can go about it either in the counterclockwise or clockwise. So I always make it a point to go about it in the counterclockwise. So we're going to go counterclockwise. We will start from A, proceed to B, to C, to D, and back to A. Now, that's what you mean by a closed network. So you got to return to the point where you start. So the electrical network is A, B, C, D, A. A, B, C, D, A. It's a closed network, and we are starting from A, proceeding in the counterclockwise direction. When we come across the battery, let me show you. When we go from there across the battery, we're going from negative to positive. So we will take that as positive V volts. Since we are going from negative to positive, we'll take it as positive V volts. And then when we go through the resistance, remember, we are moving in the direction of the current, which means we are actually flowing from the positive of this resistance, which is here, to the negative. So since we're going from positive to negative, we'll take it as negative of the product of current and resistance, because we need the voltage. And voltage is the product of current and resistance. So it's going to be positive voltage minus I times R is equal to 0. Okay, so positive V, because we're going from negative to positive of the battery, and the negative voltage across the resistance because we're going from the positive to the negative. So is equal to 0. That is Kirchhoff's loop rule. So if we give some values, like the voltage is 5 volt and the resistance is like 2 ohms, then we can easily substitute the numbers. 5 minus I times R, which is 2, is equal to 0. And then we can solve for the current. So you're going to get 2I is equal to 5. And that means I is equal to 2.5 ampere. So that's a simple illustration of Kirchhoff's loop rule. Okay? But let's try to make this a little bit more complicated. I mean the circuit. So let's say that the circuit becomes complicated. So I'm going to add some components to this. So we have, instead of one resistance, we're going to have like 3 resistors. Okay, so this is the original circuit that we had with that single resistor. And I'm going to add 2 more resistors there. So V volts is the potential difference of the source, or I'm going to call that R1 now, and then those were the points A, B, C, D, and then here is what I'm going to add. So this was the current. Let me move this faster. 5 volt, 2 ohm, so that's R1. I've added one resistance there. I'm calling it R2. I'm adding, that's 3 ohms, another resistance, R3, which is like 4 ohms. And the currents are I2 and I3. Now stop a minute. Let's look at this. So that current I1, when it reaches here, that current I1 splits into two. I2 flowing through R3 and I3 flowing through R2. Man, I should have called it I2 and I3. It doesn't matter, really. So it's I2 and I3. And what do you think is the relation between I1, I2, and I3? What's the relation? Of course, I1 is equal to I2 plus I3 because it's I1 that split into I2 and I3. Now, that is the junction rule. So at any electrical junction, the current coming in, the total current coming in, is equal to the total current going out. So we have the loop rule right there. So at the junction E, I've called this E now, at the junction E, applying Kirchhoff's junction rule, we can say I1 is equal to I2 plus I3. Hold on, we're going to use that in a minute. But now let's look at the loop. See, now first of all, notice we have 3 loops here. You could go, this is one whole loop. You could take the outer loop where you ignore R3, or we could take the smaller loop here on the side. So we have 3 loops. And we can apply the loop rule in any of those. Not in all 3 because we don't need it, like I'm going to show you. I'm taking F, B, C, E, F. So F, B, C, E, F. So the initial loop that we considered, again, you know, it's going to be 5 plus 5 because we're going from negative to positive, minus 2 I1, minus 4 I2. Wait, why minus? Remember, you're going from positive to negative. So that's why it's negative of the product of current and resistance. And here again, when we go up, aren't we moving in the direction of current I2? Yes, we are. So if you're moving in the direction of the current, it's always going to be negative, the product of current and resistance. So that's why it becomes negative 4 times I2 is equal to 0. Now let's take the loop AFEDA. AFEDA. This loop doesn't have a battery. There is no source. And we can start from, let's start from A. When we move to F, there is no resistance there. So, and then we move from F to E. Remember, we're going counterclockwise, so that way. So A to F, no resistance. F to E, we are going down, but the current is going up. Therefore, we're going to go positive. If you go against the current, it's positive. So it'll be positive 4 I2. And then you come back here, you're going in the direction of I3. See, as you go up, so it'll be negative 3 I3 is equal to 0. Let me try again. So here, A to F, no component, no resistance. When you go down, you're going against the current I2. So it's going to be plus 4 I2. And then when you come down here, no component here. And then when you go up, you're going in the direction of I3. So negative 3 I3 is equal to 0. That's what I'm going to write. So plus 4 I2 minus 3 I3 is equal to 0. Okay. Now I can substitute for I1 as I2 plus I3. Remember, I1 is I2 plus I3. That's what I substituted here instead of I1 as I2 plus I3. Then distribute this and collect the I2 terms. You can see you will get negative 2 I2 and negative 4I2, which will be negative 6I2. There it is, negative 6I2, and then you have negative 2I3 is equal to negative 5. Hold on, why do you get negative 5? Because when you take this 5 to the other side, it becomes negative 5. So you have those two equations, both of those equations, simultaneous equations, that's right, where you have I2 and I3. We can solve for them. You can substitute, but I eliminate by doing this. You can use your own method. But what I do is I multiply this with 4 and this with 6, and then add the equations. What's the idea? If I multiply this with 4, this becomes negative 24. If I multiply this with 6, it becomes positive 24. So if I add them, they cancel out. But then I have to multiply each term. Just remember that. So there is 4 multiplying, and there was 6. So that cancels out. And then remember that here you got negative 18I3, and then you also have negative 8I3. Negative 18 and negative 8 is negative 26I3, but here you got 20. So negative 20. And then solve, you get the value of I3. So I3 is 20 by 26, which is 10 by 13. The negative by negative becomes positive. So it's 0.77 ampere. And then what I do is I substitute the value of I3 into this equation. So 4I2 minus 3I3. So instead of I3, I have 0.77 is equal to 0. And then multiply that, you get that number, rearrange, and you get I2 is 2.30 by 4. Yes, that gives 0.58 ampere. Oh, now that you know I2 and I3, you can easily get the value of I1, because I1 is I2 plus I3. And so add them up. I1 is I2 plus I3, so which is 0.58 plus 0.77. That gives 1.35 amperes. So that's how you calculate the currents through the different resistors. So this question makes use of Kirchhoff's laws in order to find the values of current and voltage. So let's look at it. The question says, in the circuit shown in the figure, VA is equal to VB is 24 volts. So both of these have batteries of 24 volts. R1 is equal to R2 is equal to R3 is equal to R4 is equal to R5. All the resistances are equal, and they have a value of 100 ohms. And then to make it easier, they say the current I5 flows up through R5. Its value is 0.06 ampere. And we got to find the current I4, which is through R4. And it says assume the direction of positive current is downward through R4. So even that is given. So assume that the current through R4 is flowing down. Take that as positive, it says. So that's what's given. What do we have to find? We have to find the value of current I4. Okay. You can see several networks here, closed networks. But, you see this network, this little network here. If you apply Kirchhoff's loop rule in that network, you're going to get the value of I4. Let me show you how. So this is R1. Here are the currents flowing through the top part, which I really did not have to label, but I have. And I'm calling these junctions A, B, C, D. And I'm going to apply the loop rule in A, B, C, D. And I always go counterclockwise. So A, B, C, D, A. I don't think I've shown it. So counterclockwise like that. I can do better. All right. A, B, C, D, A. So I'm starting from A. So when I start from A and go to B, I'm going from the negative to the positive. So that's going to be positive 24 volt. Okay? And then when I'm coming down, I'm flowing in the direction of current. That means it'll be negative I4 R4, because that's I4. And then when I come here, there is nothing here. So, and then I go up. Once again, I'm moving in the direction of current, so it'll be negative I5 R5. Whenever you go in the direction of the current, it's negative. So starting from A, plus the voltage of the battery, minus I4 R4, minus I5 R5 is equal to 0. That's all. So VB, that's positive, minus I4 R4, minus I5, excuse me, R5 is equal to 0. All right, and then substitute the values of whatever we know. 24 volt is given. I4 is what we're looking for, but we know R4 is 100 ohms. In fact, all of the resistances are 100 ohms. I5 is given times 100 ohms is equal to 0, and then solve this equation because I4 is the only unknown quantity. All right, so that's 100 I4, that term, and then this one becomes 6, just 6.00, and then 24 minus 6 is 18. 24 minus 6, 18. And then when you rearrange it, I4 is equal to 18 divided by 100, which gives you 0.18 ampere. So that's the current. That's the current I4 that flows through R4. I should have labeled this as I4. I thought I did. Okay, so that's what we just found. This question has a second part. Let's go to the second part. All right, where's the second part of this question coming up? Oh. Okay, in the second part, we are asked to find the voltage V2 across R2. So where is R2 now? That's R2. We are asked to find the voltage here. Now, what is voltage? Just the product of current and resistance. So I'm going to label this as I2 and this is I3. So actually, we got to find I2 times R2, which is the voltage here. Okay. We given that I5 is 0.06. We just found that I4 is 0.180. And applying the junction rule, we also know that I4 is I1 plus I5. All right, take a look here at this junction. At this junction, I4 is coming down or flowing into the junction, while I1 and I5 are going away from the junction. So therefore, the total current coming in, which is I4, should be equal to I1 plus I5. Which gives I5, no. So we're actually looking for I1, so that was a mistake, so I've corrected it now. I1 is I4 minus I5, so we got the value of I1. All right, and then I'm going to apply Kirchhoff's loop rule in this mesh, which you can see I've not named it, but that's the mesh where I'm going to apply Kirchhoff's loop rule. And as always, I'm going counterclockwise. And when you go through the battery, you're going to the positive. So it's going to be plus the voltage of that, minus I2 R2, minus I4 R4, minus I1 R1 is equal to 0. It's pretty easy because we are flowing in the direction of the currents. So each one of them is going to be negative, right? Each one of them is going to be negative. And so you get 24 minus I2R2. Actually, we're looking for I2R2, which is V2. Minus I4R4 minus I1R1 is 0. And now it's just plug in the values. Minus, what is I4? 0.180 times 100. Okay, minus I1. I1 is right there. 0.120 times, again 100, is equal to 0. Now that becomes 18, that becomes 12, so minus 30, right? Minus 18 minus 12 is minus 30, and then you got 24, so that's minus 6, When you take it to the other side, it's going to be 6 volt. That's it. So we know that the voltage drop here is 6 volt, which is what we were asked to find. So this video simply shows you how to apply Kirchhoff's junction rule and the loop rule. So the important thing is to remember that when you go from the negative to the positive of a battery, it's plus the voltage of the battery. And then when you go in the direction of current through a resistor, it's negative current times that resistance. That's all you got to know. And then the math comes in. So I hope this video gives you more insight into solving such circuit problems, because we will have these on the exam. Thank you. See you on the next video.